Welcome to Struct Soft Center training program on design of steel structures and its connection using STAAD.PRO, Idea StatiCa and Excel. So today we are in session number two. Today we are going to discuss regarding the modeling of beams, frames and trusses in STAAD.PRO, and we are going to validate the results with manual calculations. So you will understand how you can analyze structures in STAAD.PRO. We will start from a simple beam and slowly move towards complex trusses. Static analysis using STAAD.PRO, starting with simple beams. So our first problem will be a simply supported beam subjected to UDL, a uniformly distributed load, and we will see the shear force diagram, the bending moment diagram, and the length of my beam L will be 5 meter. The UDL applied W will be 10 kilonewton per meter. E is the Young's modulus of steel. I is the moment of inertia, and these are the reactions: maximum shear force, maximum bending moment, and the maximum deflection. So these values we get as per manual calculation. I have the Excel prepared. These are our formulas for manual calculation. We will check it. So let me open STAAD.PRO. This is the STAAD.PRO which we open. When we click on new file, we can start with a new project. Let me type beams. Choose the folder where you want to save it. Choose the unit as metrics because we are going to apply kilonewton and the distances will be in meter. Click on create. So this is a blank file which will be generated. Let me also show you the manual Excel. Okay, so this is a simple beam subjected to UDL. You can see the value of reaction is WL by 2, the formula WL by 2. The maximum shear will be whatever is my reaction. Moment will be WL square by 8. I hope all of you remember these formulas. And for deflection it is 5 by 384 WL to the power 4 by EI. For deflection we require E and I. So these are the values of E and I, and here I am getting deflection. So now these are the values as per my manual calculations. Now let us validate these results with STAAD.PRO. Okay, so this is my STAAD.PRO. I want to model a simple beam of 5 meter in length. So let's start with first node 0, 0, 0, 0. This is my first node. Next node will be at a distance of x 5 meter apart. Okay, so also yes, Tushar is asking a question. Let me explain you regarding the global and local access. If you see, this is my STAAD.PRO interface window. At the bottom left corner, you can see this XYZ. These are the global axis. Okay, so if you see, if I explain you this in one note, my global axis will be always in this way. Vertically upward is my axis Y, and horizontally I have this axis X and Z. So X and Z are my horizontal axis and vertically upward is my axis Y. So these are global axis. Now whatever modeling we will be doing in this window, that will come under global axis. Like if you see in STAAD.PRO, for nodes, whatever axis we are writing, X, Y, Z, these all are global axis. So 0, 0, 0 is my first node. The next node I want at a distance of X, 5 meter. So X I will write as 5 meter and the other two values will be 0. So this is the line. Now if I want to connect them, I will just click on add beam. Click on the first node and go to the next node. So this is my 5 meter length of the beam. Now geometry is done. This is a simple beam. Now I want to apply the properties. I can go in properties. I will click on section database because I will use a standard member which is available. I am preferring ISMB 600. You can choose any member. Here I will click on Indian. In Indian S shape, I will go down and here I have ISMB 600. I will be choosing ISMB 600 and click on add. That's it. You can close this. Now ISMB 600, I have to assign it to my member. So use cursor to assign. In assignment method, I have 4 options to assign. Right now I'm using this method, use cursor to assign. It is chosen. I will click on assign. Once I click on assign, now it's written assigning. So I can choose move my mouse and click on any member where I want to assign this member. So here I have only one beam. If I click over it here, then I press escape. Then you can see it's written R1. R1 stands for reference 1. Reference 1 is my ISMB 600. So this member is ISMB 600. Okay, one more thing. When you bring your mouse on the member, you can see now the member is highlighted into 3 colors: green color, red color, and blue color. So the green color denotes the starting point of my member, and the blue color denotes the ending point of my member. Because I model my member from left to right, that is why left side is the starting point of my member and the right side is my ending point of my member. So the color is from green towards blue. So this also you have to remember. After assigning the properties, if I go in material, as I am choosing ISMB 600 and that is by default steel, so here automatically I am getting steel. So I don't need to assign this separately. If you want to assign some other material, here you have a lot of options like concrete, aluminum, steel, stainless steel, with certain grades of steel. Right now, I am keeping normal steel. Specifications. Right now, we do not have any special specifications for our beam, so I will just leave this blank. Now go in support. In support, now I want to have a simply supported beam. So I will just click on create. I will go in pinned connection, click on add. Now you can see restraint fx, fy, fz is restraint and moment is free. So this is my normal pin connection. So I'll click on add and this pin connection, again assignment method. I have 4 methods. I will choose the use cursor to assign. Click on assign. It's assigning. I will click on the nodes 1 and 2. So both the nodes are now pin connected. Again, I can press escape. Support is also done. Now I will go in loading. In loading, I have three options: definition, load case detail, and load envelope. I will click on load case detail. Then I will click on add. Let the name be load case 1, the default name. Then I will click on add and close it. So I have created a load case in my load case detail, that is a load case 1. Click on load case 1 and again click on add. Here I have various methods of loading what I can apply on my structures. So right now I am interested in member load. So I will click on member load. Here you can see the figure. I want to apply a uniform force, uniform UDL. The value of uniform force is minus 10. Why minus 10? Because the direction of my loading, here in directions you have these options: X, Y, Z, local. So these will be applied as per the local axis. I have not explained you local axis yet. I will explain you shortly. Second option is GX, GY, GZ. These stands for global axis. So right now I want to apply my force in global Y axis. So that's why GY is chosen. And I want to apply the force in downward direction. By default, GY is upward in direction. I want to apply force in downward direction. So I will just write minus G, minus GY, simple. So if this is the force what I want to apply, so this will be minus GY direction of force. Minus 10. I can just click on add and close. So here you can see question mark. The force has not been applied yet. Click over it. Assign, use cursor to assign. Assign. Yes. Now the UDL has been applied. This we have also seen yesterday, but today we are going to see the results. Next, go in analysis. Define commands. Perform analysis. No print. Add. Close. So this is a normal analysis command. That's it. Designing, right now we are not going into designing, we are only following up to analysis part. So I hope this is clear to all of you. This is the first example, so I'm making it slow. Okay, so now let me also explain you regarding the local axis. So if you right click and go into labels, in labels you have option structure, no, show axis at origin. Let's try, apply. Okay, this is your global axis. Show axis at origin, apply. I want to see the local axis. Let me see, where is it? Full section. If you click on structure, 3D full section and click on apply, the section what you have applied that will appear to you. Okay. If you want section outline, again click on section outline, apply. Only the outline will be available to you. But let's go with none because that creates disturbance. Beam orientation, apply. Yes. If I click on beam orientation will tell me the axis of my beam. Okay. So this is what I was looking for, beam orientation, to see the local axis. Now if you click OK, now let us zoom on this part. You can see these three, four colors. Let's take screenshot. I'll explain you. Now these are the local axis. So in local axis, here the XYZ axis is not written, but the color is shown. So you have, let's take with blue color. You have blue, you have green, blue, red, green. Blue is your X axis local, red is your Y axis local, and green is your Z axis local. Okay, so these are local axis. So if you see, this is my member. For example, this is my I section. Vertically upward, this is my Y axis. Horizontally, this is my Z axis. And along the length of the member, that is my X axis. Similar to what you see in global axis. But global axis is permanent. Local axis, however you change the orientation of your member, this will be the local axis. If you have this column in vertical direction and the column is maybe like this, okay, if you have this kind of I section column, now in this, along the length of the member, this will be your X axis. In this minor direction, length of the, in this along the height of the member, this will be your Y axis. And in major bender direction, bending direction, this will be your Z axis. So anyway, whatever is the orientation of your member, now assume this is your another member. Again, for this another member, this will be your I section. Throughout the member, this kind of beam you will be having. Again, in this, along the length of the member, you will have your X axis. Vertically upward, along the height of the member, you will have your Y axis. And in this direction, you will have your Z axis. Okay. Now I want everyone to tell me in the comment section, is local axis and global axis clear to all of you? A very important topic. Tell me in the comment section. Yes. We are going a little slow, but once we understand these basics, we will move quickly. Okay, now this is fine. Display whole structure. If I click, I will be able to see my whole structure. Now I don't want to see this orientation always. So I'll give right click, labels, beam orientation, I'll untick and okay. So that is gone. Okay, loading I have applied. I have applied the loading of, if I click on that loading, that will be visible. If I want to see the value of this loading, I have another option, right click, labels, load value. If I click on load value, apply, okay, the value of load will be written over here and it will be visible to me. If I want to see this from front view, in this cube you can see, if you go in cube view, you have these all the cube options. Here if I click on this central cube, this is front view. If I click on top, this is my top view. If I click on this is my back side view, this is my side view. So these are all the orientation. This is my isometric view. So I'm interested in the front view, so this is my front view. The my beam is subjected to UDL of 10 and the value and the length of my beam is 5 meter. If I want to measure the length of the beam, I can go in utilities, nodal tool, node to node distance, from first node to second node. I can click and measure the distance. This is 5 meter. Again, I can go in node tools and remove node to node distance. If I directly want to measure the distance without clicking on it, beam tools, dimension beam, display. So again, you can see 5 meter. Remove, remove, close. So I have shown you two methods how you can measure the length of the beam from node to node or from the beams. Now I want to analyze this and check the shear force diagram, bending moment diagram, reactions, deflections. So go in analysis, run analysis, save. So this run will be performed. You can see zero errors, one warning, one note. I'm getting one warning. I will be explaining you regarding that warning shortly, but first let's see the results. To see the results, you can click on post processing. Okay. So in post processing, this window will appear to you. Okay. At the top end side here, you have results. In results, deflection is there, displacement is there, utilization ratio is there. This will only be available after you design your member. Right now, we are not designing. I only want to see the analysis. So displacement, you can see this is the, if I press the control button and move my wheel of my mouse, you can see the displacement. So this green part is my deflection of the beam. This red black is my original beam and this is the deflected shape. If I want to see the value of deflection, I can go in anoid, beam results, displacement, anoid, close. So now the animation is done. The value of maximum deflection you can see is 0.437 as per STAAD.PRO. Now let us validate this result with manual calculation. In my manual calculation, the result was 0.44. So this is validated, right? Next, I want to see the shear force. Okay, anoid. I will remove this. Again, if I click on displacement, that will vanish. Now, before explaining you these values, let me explain what is this. I will take the screenshot. These are 6 parameters what I can measure in my beam. And this is my beam. Let's do it red color. This is my beam. How are the axes of my beam? If I explain you the axis, this is my I section. It can be any section. Right now I'm considering I section. Okay, let's do one thing. I will bring this over here. This is my I section of my beam in this way along the length. Okay, I tried to draw the 3D model of the I section. I hope this is clear to all of you. This is better. Okay, now in this axis, I will draw with this yellow color. This is my x-axis, vertically upward is my y-axis, and horizontally in this direction is my z-axis. If I try to show you in this cross section, this is my beam, vertically upward is my y-axis, horizontally is my z-axis, and along the length of the member is my x-axis. I hope this is clear to all of you. Now Fx. Let's do this with purple color. Fx is my axial force in x direction. So whatever axial force I get, Fx is my axial force along the length of the member, right? Next point, Fy. Fy is my shear force in y direction. So Fy, or I can say major direction. Shear force, major direction. Fz is my shear force in minor direction, right? Here you can understand, if this is my cross section, okay, or if I show you over here, if this is my cross section, whatever shear force I will be getting over here because of UDL, this kind of shear force, this will be my Fy. It is in major direction. But if I am getting some shear force, I am applying some lateral force on this beam, and because of this lateral force, the beam is subjected to some shear force in this other direction, like this, maybe like this. I hope you are understanding. That is the shear force in minor direction. That I will be that will be labeled as Fz. So Fy is uh, Fy. Sorry, Fy is your shear force in major, and Fz is shear force minor, and Fx is your normal axial force. I hope this Fx, Fy, Fz is clear to all of you. Now coming to the moment. First, let us see My, not My. Let us see Mz. Mz is your moment in major direction. Let me shift this. You have Mx, My, Mz. Mz is moment in major direction. How? I will explain you. Whenever we are saying moment, we are saying about z axis, about y axis, about x axis. So if this is my uh, structure, right? I will remove this red part, or yeah, let it be. Every one of you are aware of your right hand thumb rule. If you place your right hand along the z length, okay, now you have to do this visually. Place your thumb along the z axis. If you place your thumb along the z axis, the fingers will show you how your member will be bending. So if I place my thumb, let me draw this. If I place my thumb like this, my fingers will be like this, right? So it shows that this kind of bending, normal bending of my beam. Tell me, is this clear to all of you? This is my bending of my beam. My beam will bend like this. Major bending. If this is my member, UDL is applied on this. This will bend like this. This will bend. If you see the cross section, this is Z, this is Y, and along the length is X, and it is bending about Z axis. This is called MZ, bending about Z axis. So moment major. Next thing, My. My, if you place your thumb, let me choose another color now for Y. If you place your thumb along Y, if you place your thumb like this, now your fingers will be like this. Okay, the thumb is not clear, but I hope you are understanding. This will be bending about minor axis like this. In this, you will not be able to see. If you want to see this bending, if you want to see through plan, this is the top view. This was front view. Right now, I am seeing this from top view because of the UDL applied on this from top view. This will bend in minor direction. If because of wind coming, maybe some wind is coming like this. Because of this wind, there is some minor direction bending about the axis. So this is your minor bending. So this is called moment minor. And the third option is your MX. MX. Now this is torsion. What is torsion? When there is, if you place your thumb along the X axis, now your thumb is like this, and now the bending is like this. Twisting of your member. So this is your eye section, and now this is rotating and it is becoming like this. Twisting and it is becoming like this. So that is moment, or you can just say torsion moment. This is bending moment minor, bending moment major, or it is also called as moment minor, moment major. Tell me, everyone, are these six terms clear to all of you? I want everyone to answer. Tell me, are these six terms clear to all of you? If you have any question, you can ask now. Okay, let me again explain. Generally, in 2D, I'm drawing. This is my simply supported beam. This beam is subjected to UDL. This is my current case. If I see this cross section, if I see the cross section, this will be like this. An I section subjected to some UDL. Now, if I draw the axis, this is my Y axis, this is my Z axis, and along the length is my X axis. So right now, along the length, this is my X axis, vertically upward is my Y axis, and in the other direction, that is my Z axis. Is this two terms clear to you? This is the view when I see from 3D. But if I see the cross section, this is my cross section. When I see the cross section, these are the axes. Now what is happening? Because of the load applied, this will just bend like this. And this, how it is bending? If I place my thumb along Z, if I place my thumb along Z axis, then this is the direction of my fingers. So this is called major bending. Normally, when load is applied and my member is bending, this is major bending. But similar case, if this is your eye section, or let's not take eye section, I will just take a normal rod, cube, a small cube. In case 1, it is subjected to this black force, UDL. Because of this UDL, this is bending like this. This is my MZ. In second case, there is my wind force acting on this bar. Because of this wind force acting, this member is also bending like this. This is my MY. And there is some twisting moment also trying to rotate my beam. Because of this twisting moment, there is some kind of moment like this also. This is twisting in this way. There is some twisting happening. This twisting moment is called mx. I hope this is clear to all of you. If still you are not able to understand, let's continue the session. Maybe after few sessions, you will understand what we are doing. Okay, we have invested a lot of time. Now I hope throughout the course and throughout your life, you will not have any problem with these mx, my, mz, fx, fy, fz. Now, if you want to see the result, if I click on Fx, I will not have any actual force. Why? Because my member is only subjected to UDL. Now, my case right now, it is only a beam where it is subjected to UDL. So, Fx is 0. Fx will only come when I have some kind of axial force like this. Right now, I am having only UDL, so this will not come. Fy shear force in major direction that I should get. So if I click on Fy, you can see this is my shear force. If I want to see the value of shear force, I can click on annotate, beam results, shear maximum, annotate, close. So maximum shear force is 25. This I am getting, and the figure is also triangular. If you want to validate this, you can see shear force is triangular. Now quickly I will explain you this also. If you have a beam which is pin connected and it is subjected to UDL, reactions will be of course like this. The shear force diagram will be this, and this, because of UDL it will come down and go up. Bending moment diagram will be in this way. If you want to see, Fy is shear force, Mz is bending moment. Mz is your bending moment, right? Fz is your shear force in minor direction, that you will not get. My is bending moment in minor direction, that also you will not get. Mx is torsion, that also you will not get. So in this figure, you will only get Fy and Mz, the shear force and bending moment. If you want to see the value of bending moment, annotate, beam results, bending moment, maximum, annotate, close. The maximum bending moment is 31.25. So if you go back to the Excel, it is 31.25. So this is also matching. Shear force 25, this is also matching. Now if you want to see the reactions, you have this second tab. Let's untake this. If you click on reactions over here, here you get the reactions. X is 0, Y 25, Z 0. Moment is free. Same over here. So reaction is 25. So reaction 25 is also matching. Okay. Now tell me everyone, is this clear to all of you? Everyone please answer and tell me, is this clear to all of you? Simple. We understood how you can see the reactions, how you can see shear force, bending moment, deflection, and we also validated the results with manual calculation. Now quickly, we are going to see for other cases. My next case is point load. Okay, the direction of bending moment. One of you is asking, in some books the bending moment is shown like this. So this is fine. This is just the orientation, whether you are considering y as upward as y or downward. So, and some shear force may also be seen like this. So the orientation is fine, but the overall figure should be similar. So it can be, some books also give this kind of shear force and this kind of bending moment. That is also correct, and some give in this way. So anything is fine. Now I have my second case. Simply supported beam subjected to point load. Because of the point load, again you will have same reactions, and now your shear force will be like this, and your bending moment will be like this, straight line. Let us check. Go in your model, analytical modeling, loading, add, load case 2, close, load case, add. Now I will go in again, member load, concentrate force. Concentrate force, again the value is 10. Okay. So minus 10 in global y-axis. Click on add, close, choose concentrate GY10, use cursor to assign, click on this, you will have this point load. Okay, this point load is there. Escape. Again go in analysis and design, run analysis, save. Again one warning you are getting. Now let me explain you the purpose of this warning, the reason for this warning. Right now we are working in two-dimensional object. So STAAD.PRO, STAAD by default will always work on 3D. STAAD will always work on 3D, which is denoted as space. We want to work in two-dimensional. So we need to mention to STAAD.PRO that we want to work in two-dimensional. And two-dimensional, the word is plane. Plane stands for two-dimensional. So you need to mention this command to STAAD.PRO that you are working in plane. Otherwise, by default, always STAAD will assume that you are working in space. So how to mention it? Go back to your STAAD.PRO, utilities. Here you have the option command file. Click on command file. Once you click on command file, this window will appear to you. So whatever you do in STAAD.PRO, whatever commands you type in STAAD.PRO, that all gets converted in some kind of codal language, and that codal language is written over here, because computer only understands the language of zeros and one, and whatever you do, that is converted into some code, and that code converts all your input into some machinery language. So this is the brain of your STAAD.PRO. So here the first line you can see STAAD space. So this space you need to delete and write plane. If you are working in two-dimensional elements, two-dimensional members, two-dimensional structures, you need to mention STAAD plane, and you can just close this. Save. Simple, nothing has changed. Again, go in analysis and design, run analysis. Now, ideally, you should not be getting any warnings. Yes, zero errors, zero warnings, zero notes. Now you can go in post processing. Now you have two load cases. Okay. So first one, if you go over here in loads, here you have the drop down, load case 1, load case 2. So right now I'm choosing load case 2, the point load, and view. I want to view this from front view. Results, Fy. You can see the shear force. Now one more thing. You can see this kind of cut over here, this kind of inclined thing over here. Okay, let me also quickly explain you this part. Generally, what happens whenever you work in STAAD.PRO, I think this is not necessary. Whenever you work in STAAD.PRO, STAAD.PRO, what it does, this is your member, you are analyzing. STAAD.PRO will divide this member into certain number of parts. Each member is divided into certain sections. I think that is 10 sections. Let me just quickly check. You don't have to pay attention to this. I'm just checking it. I will be explaining you all these points later on. Perform design at ends and 1/12 of the section. So every member in STAAD.PRO, when it is designing, it divides your member into 12 parts. And for each node, the analysis is done. For example, this is my member now. I have divided into 12 parts. Let us assume these are some 12 parts. So for each point, it will check. Okay, so for this point, the shear force is maybe 25. So it will mark 25. Next point, shear force is again 25. Here also it is 25. In my manual calculation, how it is coming? It is coming like this. So here I have applied some point load. So wherever you are applying this point load, at that point, this is my point load. Wherever I am applying my point load, at that point, there is sudden drop in shear force. This is my manual calculation, right? But STAAD.PRO is calculating over here, over here. Let's assume this is another node and this is another node. You don't have any node over here. So here it is 25, here it is 25, like this. Now it is directly measuring over here. Here it is saying minus 25, minus 25, minus 25, minus 25, 0. But now from here to here, it is just drawing a line. So that is why you see this inclined part. But actually it is like this. Sudden drop at node and then this. Tell me, is this clear to all of you? This is the error in STAAD.PRO. If you want to have correct solution, then you can just mention do the calculation in 13 parts. If it does the calculation in 13 part, there will be one node at the center, and then it will come like this, like I am showing in purple color. Sudden drop. Okay, I hope this is clear to you. That is the reason you are getting post processing this thing. Okay, MZ is okay. MZ I am getting in this way. So let us see the values. Anoid, beam results, bending maximum, anoid 12.5. Shear force, anoid, bending moment maximum, anoid close 5. Displacement, anoid, bending beam results maximum resultant, anoid close 0.141, and reactions 5. So this is the case. Reaction 5, bend shear force 5, bending moment was 12.5, deflection was 0.14. Third, I will show you how you can do for uniformly varying load in this way. So go to your model. Just confirm me, is this clear to all of you? Quickly, yes. Tell me yes or no. Loading, load case details. Now let's go for third load case 3. Add. Do you want to change the result? Yes. Close. So now load case 3. Click on add. Now I want to have the member load again, but uniformly varying. So trapezoidal load. So if you click on trapezoidal load, W1 will be 0 and W2, the other end will be minus 10. Is this correct? What loading I have chosen? Yes, 0 to 10. Yeah. Again, global Y, add, close. So this, use cursor to assign and choose your cursor. That is being applied perfectly. Analysis and design, run analysis. We want to save the model? Yes. Done. Post processing. Okay. Load case 3. Deflection. Let us check. Maximum resultant 0.219. What we are getting over here 0.22. It is matching. I'm doing now quickly because these are all repetitions now. Shear force, you can see this kind of curvature you are getting. Anoid, bending moment, shear force maximum, anoid, close. 16.67. 16.67. Okay. I will be sharing you this Excel. You can try all other things. Bending moment, you can see in this way. Bending moment maximum, anoid, close. 16.035. 16.03504. And finally, what else do you have? That's it. Reactions. Okay, go in reactions. Now you can see at one end the reaction is 8.3 and at the other end the reaction is 16.67. Go to your Excel. 8.3, 16.67. So these are also matching. Okay, so we have seen UDL, we have seen uniformly varying load, we have seen point load. Akash is asking what to do when the command file option is shown inactive. I don't know what you are telling. What is the command file? If you are speaking regarding this design, this command, right now, don't focus on this. This we will be studying later on. Okay, so now next thing, what I will be doing, same thing, but one end will be fixed. The support condition I will be changing. One end will be fixed, other will be pin. So go back to your model, loading supports. Sorry, one end I will change to fixed support. So create fixed support. At fixed support, what will happen? There will be moment which will be generated. So fixed support is my this. Use cursor to assign. I can overwrite my existing support. So if I click over here, this support will change now to fixed. Escape. Okay, so this is my fixed support at one end and pin support at the other end. So again, go in analysis and design, run analysis, run the analysis. Okay. Now go in post processing. I am doing quickly. If anyone has any query, you can ask or type it in the chat box. Post processing. Okay. So I want to check for what is the case I want to check for UDL. So for UDL is my load case 1. So for my load case 1, if I see shear force, you can see the shear force is more at this end and less at the other end. Displacement we will see later. So anoid beam result maximum anoid close. So maximum value is 31.015. 31.25. Okay, so slightly matching, not exactly, but slightly matching. Next is my MZ bending moment. You can see because this is my fixed support, I will have some bending moment over there, and this will be my figure. Anoid beam results bending maximum anoid close. Maximum bending moment is 30.074. Bending moment 31.25. I will tell you why you are getting this difference. 31.015, 30.074. Okay, shear force and bending moment. Next thing is reactions 18.98 and 31.015. 18.75, 31.25. So actually, this all I can give yellow. They are not perfectly matching, but slightly, maybe 1 2 units here and there. Displacement, anoid, beam results, displacement, anoid, close 0.19, 0.18. So these are all slightly matching. The reason behind this not matching completely, now this is your indeterminate structure. This was your determinate structure. There was only two reactions, two supports, two reactions. So values were exactly matching. But for indeterminate support, you can see over here, for fixed support, you have three reactions. For pin support, you have two reactions. Total five reactions, five equations, and reactions are also five. So you do not have five equations. You only have three equations. So because of this, you need to use some other stiffness matrix method and some other methods. And because of those methods, the values are heavily impacted because of the stiffness of the member. So depending on the stiffness, the values, the manual calculation do not match 100%. But the STAAD.PRO values are accurate. The manual calculations are approximate. So you can see they are slightly different. Okay, in utilities command file. Okay. I hope this is clear to all of you. Let's go back to analytical modeling. If you go in utilities, the command file, it is active over here. Command file. This is the command. Close it. Generally, this should be active. If this is not active, you can click on the window and it will become active. Okay, I hope this is clear to all of you. Now let's move to the next example. Same thing with a point load. So this we have already done post processing. This is load case 2 with a point load. Now quickly we will only see the shape. You can see the value later on. Shear force is matching. Bending moment shape is also matching. You can see shear force, bending moment. Okay. So simple thing. What you need to understand, when let's make this in red color. When you are making this as fixed, when you are making this as fixed, what is happening? Shear force is becoming slightly more over here. Shear force is becoming slightly more over here because this is fixed support is attracting some more shear force. And bending moment, you are getting some bending moment over here like this. You are getting some bending moment over here like this. Okay. Third option is fixed at both the supports. Now what I am doing, analytical modeling, support, support 2, I want to assign, use cursor to assign, and here. Yes, the both the supports I am making fixed and I am running this analysis again. Okay, now this is both fixed supports. Post processing. Okay. Shear force you can see almost similar. Bending moment you can see in this way. Both the supports you are getting some bending moment. Load case 1 also will be similar. Load case 3 also will be similar. So you can check these values. Figures it was almost matching. The values you can validate at your own. Okay. Next option was cantilever. One end is fixed, other end is cantilever. So let us also check that. Analytical modeling. Support. So cantileverment one end should not have any support. So first option is no support. Use cursor to assign. Assign. Let's assign to this. Yes. Again, you can go in analytical modeling and run the analysis. Done. Post processing. Okay. So what are the options? UDL and point load. Now point load is at the node. I also want to show you that. Analytical modeling, loading, add load case 4, close load case 4, add nodal support. So this was member load what we had seen. You also have nodal load. Nodal load Fy minus 10 and click add close. So this Fy you want to assign at this node. Use cursor to assign and at the end node. Now you can run it. Done. Post processing. Okay. Here you have your shear force. Here you have your bending moment. Values you can validate it. You can see shear force, bending moment. Here in addition to that, a moment is also applied. You can see M moment is also applied. That how to apply? Let's see. Loading. Load case 4. Double click on this. Shear force and moment. Moment will be mz. Maybe minus phi. Assign. Okay. You can see this moment is also applied. It is similar to this moment. Yes. Load of 10. I don't know what moment is applied. I will assume moment is also applied of 10. So let's try minus 10. Change. Let's run and see. You can validate the results. I will be sharing you the Excel. Yes. Yes. So I explained you shear force bending moment. Same thing you can do for overhang beam. Overhang beam, let me, maybe you need to model this. What is the length? 3, 4, 3. Okay. Analytical modeling. First is at a distance of 3 meter, 3. I'm changing this. Next is 4 meters. So 3 plus 4, 7. And next is at 3 meter again. So 7 plus 3, 10. So these are the members. Add beam. You need to add the beams. Properties. Let us assign the property ISMB 600 assigned to selected beam. So you can select all the beams. Assign to selected beam. Assign. Yes. And support is pin support. Use cursor to assign. This is first pin support. This is the second pin support. If you want to see the node, you can press shift K, then nodes will be visible to you. After this loading, I want to apply a UDL. What is the value of UDL? 10 kilonewton. Load case detail, first case UDL. This I want to apply on all the members. So you can just click assign to view. First one. So for the whole view, this UDL would be applied. Yes. Now you can run the analysis. Done. Post processing. Okay, you can see this is the shear force, this is the bending moment. It is matching with the shear force and bending moment. Larger the central span, larger will be the moment. Now, if you have this kind of beam and it is overhang like this, subjected to UDL, bending moment can be like this, or it can be like this. Yes, this depends on the span, the central span. So right now, because my central span was less, it is like this. If I increase the central span, let's make this as 10 and 13. Loading UDL, I think it will be the same. Yes, now if I run this, if you have any question, you can ask. I am doing it quickly because now I have shown you initially many problems, simpler ones. Now I am doing a little faster. Now you can see the bending moment is sagging down because the length is more. Same thing you can do for continuous beam. You can try this on your own. Okay. Next problem. I will close this. Don't save. After beams, we can move towards frames. Portal frames subjected to point load, subjected to moments, subjected to UDLs. Before moving towards frames, tell me, did you understand all kind of assignment methods for your beams, assignment methods for your loadings, load assignment method, support assignment method, member assigning methods? Are all these points clear to all of you? You can answer me in the comments. Tell me, is this clear to all of you? Kindly answer, tell me if everything is clear to all of you. Everyone, quickly answer. Yeah, Rama Arjun, I told you the direction changes because certain books assume positive upwards. In STAAD.PRO, it may be different. So direction is not an issue, but the shape should match. The shape should be matching. Direction is not an issue. Tell me, should we continue with frames or should we continue with frames from tomorrow? We have frames and trusses. Okay, I want everyone to tell me, should we continue tomorrow or continue today? Okay, beams with complex loading. You are, Saurabh, you are telling regarding. Okay, I'll explain you, I'll show you some complex loading as well. There is one beam from column to column, then how we model overhang beam on that. These are very simple. So, Tushar, we will tomorrow when we will be discussing frames, I will show you how you can model columns, beams all together. Frames we can start tomorrow. Today, let us explore some other methods of assigning loads. Okay. So if you go in load case, let's create a new load case. load case phi. In load case phi, okay. So first option is self weight. So whatever is the self weight of your member that you can add. This I will be explaining you again in detail when we study our warehouse. Next option is nodal load. I explained you how you can assign nodal load. If you want to apply load in x direction, you can go for fx, fy, fz, mx, my, mz. Let's try this. Let's go with minus 10. Add, close. Fx, use cursor to assign. If I assign over here, yes, you can see. If I assign at this point, this kind of load is applied. If you want to, if you choose toggle load, so toggle load means it will remove the load which is assigned. If I click on toggle load and if I click on this point again, then this load will be removed. Toggle is just inverse of assigning. Okay, again if I click here, toggle load, this load will be removed. Again if I untick this, load will be applied. Okay, and another option is assign to view. If I click on assign to view, for all the nodes that load will be applied. Let's see, assign. Yes, I have 4 nodes. So for all the nodes that load is applied. But if I don't want to assign, so toggle load, assign to view, assign. So from all the loads that load is removed. So this is the way. So use cursor to assign. Let me assign only on one part, this node. Yes. Okay, so from tomorrow we cannot start early, but we will start exactly at 8 a.m. Okay, we will start exactly at 8 a.m. and we can end by 9:15, 9:30. Okay, so this is some of the methods. Add, what else load cases you have? Nodal load case you saw, member load case, uniform moment. If you want to apply moment, you can use this option, concentrated force, concentrated moment, linearly varying load. This we have seen. Trapezoidal load, this also we have seen. Hydrostatic pressure, these are not important for our case. So 1, 2, 3, 4, 5, 6, this we have seen. Apart from that, area load, floor load, these all things I will be explaining you later on when we need them. Right now what is important is nodal load and member load. So these two we have seen. Almost all the major ways of applying load we have covered. So I think Tushar, some of the complex method also we saw today. So from tomorrow, I think Saurabh had asked that question. Yes, okay. So from tomorrow, we will start with frames and we will also conclude the trusses tomorrow. Frames and truss we will see tomorrow. Today, I think this will be our end of this session and we will see tomorrow.